a planar triangle, or plane triangle, or if you prefer, a flat triangle, unless you're looking at this on one of those fancy curved TV screens. For the sake of this, this is considered to be a flat triangle. And today we're going to find the centre of it, which immediately runs into an interesting question of which centre. How do you define the centre of a triangle? Let's start by considering just one side of it there, just that one longest side. Now, around each end of it, I have drawn sets of arcs. Largest red arcs, smaller orange, smaller than that yellow, and so on. In this case, I have drawn the same radius of red arc from both ends on both sides. You don't actually have to say use the same radius up in the top right as you do down in the bottom left in this example. What matters is that you use the same radius from both ends. You get crosses where circles are crossing each other. A circle around the point in the top left, a circle around the point in the bottom right. A circle being defined as the set of points that are equidistant from a particular point, its centre. A circle centred on that top left corner of the triangle is a set of points that are equidistant from it. If you draw a circle, or a part of a circle, an arc, with the same radius, centred on the other end of that side, the rightmost point of this triangle, you get a set of points that are that same distance from that corner. Where those two arcs cross over is a point that is that same distance from both of those. Whatever radius you use, on whichever side of the line you draw your two arcs, as long as the radius is the same around each vertex of the triangle, where they cross over is a point that is equidistant from the two vertices of the triangle. As you can see, if you draw a straight line through all of them, if you draw a line through all of those intersections, it's going to be a straight line. If you look at the greenish yellow, the slightly bluish green, the slightly turquoisish green closest to the white line, making that kind of pretty fairy turn shape, you can see where the lines cross there, they're not at a right angle, they're crossing quite a shallow angle. If I got even close to the line, the angle would be even shallower. It would be hard to see exactly where they cross over. Likewise, if I go miles out off the edge of the diagram, you'll get the same problem. But if we look at the yellow ones, those are crossing at approximately a right angle, or the yellowish green ones. If you go for a radius that is about 70% of the side, you get pretty much a right angle. With any two of these crosses, you don't have to use all of them, just any two, just draw two, you can draw a straight line which goes in between the two ends of that side of the triangle and is equidistant from them all the way along its length, which means it's going to cross that side of the triangle at a right angle. You have drawn the perpendicular bisector of that side of the triangle. That yellow line goes through all of those crosses and cuts that side of the triangle in half, bisects it at a right angle, perpendicular. One perpendicular bisector. You can do the exact same thing on the next side of the triangle and on the final side of the triangle, giving you 3 perpendicular bisectors. And if you draw all of them in, you find they all cross over at the same point. A curious feature of a triangle, that when you draw these lines in, they all cross in the same place. And that point, because it is on the yellow line, you know it is the same distance from the top left as from the right. Because it is on the purple line, you know it is the same distance from the right as from the bottom left. Because it is on that cyan line, you know it is the same distance from the top left as it is from the bottom left. So it is the same distance from all 3 points of the triangle, which means you can draw a circle around that point like that. Doesn't have to be in that colour scheme. I just thought I'd use that to make it pretty and distinctive and fabulous. And there you can see the circle on the circumference of which the 3 points of the triangle lie. The circle. Might hear it called an out circle. Get it? Out. Right, never mind. So there we have the circumcenter, the centre of the circumcircle. You'll notice that is the centre of a triangle that's actually outside the triangle. Maybe we want to be inside. Let's go back to our triangle, and instead of looking at one side, let's look at 2 sides and the angle between them. If I draw arcs around that top left point, crossing both of those sides, I get pairs of points on the sides equidistant from that vertex. I can then use those pairs of points, the red, orange, yellow and green here, to draw more arcs. From the red arcs, where the red arc crosses the white line of the side of the triangle, I have drawn this violet, magenta and indigo set of 3 crosses. And you can see the violet is at quite a wide angle, the indigo is at pretty much a right angle. From where the green crosses the side of the triangle, from each place where the green arc crosses a side of the triangle, I have drawn the cyan, aquamarine, navy and again indigo arcs, smaller and smaller around those points. And you can see we again have a straight line of crosses. The cyan one may not be much use because they're crossing a long way from a right angle and it's kind of hard to pick an exact point. You get somewhere near, but all of them put together give you a pretty good straight line. And it ought to be visually obvious here that it's cutting the angle in half. Each of those crosses is at a point that is equidistant from 2 points, one on each side of the triangle adjacent to that angle, which are themselves equidistant from that vertex. Therefore that straight line is halfway between the 2 sides the whole way along. You're using the vertex as the cross on one side and your constructed cross as the cross on the other side to create the perpendicular bisector of a line crossing the triangle from where the red arc intersects one side to where the red arc intersects the other side, or the green arc, or the orange arc, or the yellow arc, whichever. A perpendicular bisector of a line that's going across that angle splits the angle in half. You now have an angle bisector, which I can draw in there in shiny yellow. And of course we can do the same thing for the next angle. The cyan line there is an angle bisector at the bottom left vertex, and the purple line there is the angle bisector at the bottom right vertex. And yet again, if you put all 3 lines in, you find they all cross in the same place. Now, instead of being a set of points equidistant from 2 vertices, each of these coloured lines is a set of points equidistant between 2 sides, between the nearest points on 2 sides. Which means if you draw a circle anywhere along any of those coloured lines, it's going to touch the 2 adjacent sides at the same time, at the same radius. Where they all intersect, a circle centred on the purple line is equidistant from the upper right side of the triangle and from the bottom side of the triangle. A circle centered on the yellow line is equidistant from the upper right side of the triangle and the left-hand side of the triangle. A circle centered on the cyan line is equidistant from the bottom side of the triangle and the left side of the triangle. If it's on all three lines, it is the same distance from all three sides of the triangle. And you get the fabulous in circle. We have constructed, the in centre. So we now have two centres of the triangle. We notice they're in different places, one inside and one out in this example. One that is the centre of a circle that touches all three vertices, one is the centre of a circle that touches all three sides. Nice, we don't have to stop there. I can use this vertex in the bottom left as the radius. Sorry, I can use the length of a side as a radius. I can centre a circle on the vertex in the top left with a radius, length of the side to the bottom left, and that gives me one of these red arcs, the one centred on the top left vertex. I can also draw a red arc centred on this right-hand vertex, whose radius is the length of the bottom side. So this bottom left vertex is an intersection of those two arcs. By drawing in the arcs, I've found another intersection of them, the other side of this top right longest side of the triangle. Instead of the perpendicular bisector here, I have found a bisector that goes through that vertex. In effect, this red cross is at the reflection of the opposite vertex in the nearest side. And I can draw in that line as a yellow line through the vertex and through the red cross, crossing the top right longest side at a right angle. Exact same approach, a couple of blue arcs. In this case, this is the reflection of the top left vertex in the bottom side of the triangle. Little thin white line extending that bottom side, and the cyan line from the top vertex down through that cross intersect at right angles. Outside the triangle, mind you, but it is still a line from that vertex and perpendicular to the opposite side. Through that vertex, perpendicular to the opposite side, or a demi-line from that vertex, perpendicular to the opposite side. Either description works. You might want to go with the full line, or at least a line segment that goes all the way across the paper. Third side, third vertex. Again, extended the side of the white line. This time we have a purple perpendicular to it from the rightmost vertex, perpendicular to the left side, off to this green cross, or through the green cross and beyond. And again, all three of those lines intersect in the same place. It's down here, well outside that triangle, on the other side from the circumcenter. And this is, well, it's a place. It's called the orthocenter, because each of those coloured lines is orthogonal to a side of the triangle. And it is a place from which your line of sight to a vertex is perpendicular to the side opposite that vertex, because that's how we constructed those lines. If anyone knows an actual use for it, put it in the comments, because I don't know one. Next up, just keeping that yellow line, but copying the triangle and the yellow line and flipping it 180 degrees and making another copy of that, I can put them together into this shape, where you have the original triangle in the middle with the yellow line through it, and you have a copy of it at each end of this shape with its own yellow line. You can see the yellow lines are parallel, because a 180 degree rotation of a line doesn't make much difference. And then I can remove or ignore parts of it, and you get this shape. From copied yellow line segment inside the triangle to copied yellow line segment inside the triangle, and between the longest side of the original triangle and two parts of the, well, one part of each of the, let me try that again, one part of the longest side of each of the two copies of the triangle, you get a rectangle. Now we know that the greyed out triangle in the top left is a copy of the long part of the original triangle, and the greyed out triangle in the bottom right is a copy of the other part of the original triangle. So those two together are the same area as the original triangle. We know that the part that isn't greyed out, at the bottom of this rectangle, because it's at an angle, is a copy of and has the same area as the long part of the original triangle, and the non-greyed out part of the top left, the leftmost triangle, which is the left side of this rectangle now, is a copy of and has the same area as the short part of the original triangle. So this rectangle has twice the area of the original triangle. And we know the area of a rectangle is base times height, or length times width. We can call it base times height. We can call this long side the base and the length of the yellow line the height. Seems fair. Gives us an area. So we know the area of a triangle is a half the length times the height. Colour it in to make it a little more obvious. Green triangle and two-part blue triangle have the same area. Therefore, the green triangle is half the area of the rectangle. If we know that the area of the triangle is half the area of the rectangle, when we go back to this circumcircle, where we have these lines that cut the base in half, whichever way up you have this triangle, one side is the base, the current way up, the purple is cutting the base in half. If you view the long side as the base, the yellow is cutting it in half. If you view the shortest side as the base, the cyan is cutting it in half. And we can ignore most of those lines and just go down to these little bits here. We have a little bit of magenta cutting one side in half, a little bit of yellow cutting the other side in half, longer side in half, a little bit of cyan cutting the shortest side in half. So we now have, whichever of these sides is the base, half the base each side of that bisector. It is a bisector, that's its whole point. Half the base times the height is the area. Well, if you have half the base, then your area is going to be half of half the base times the height, but it's still a triangle with the same height. You've just halved the base, so you've halved the area, right? So if you keep the same top, same vertex of the triangle, opposite one of these bisectors, and cut from that vertex to where the bisector bisects the line, otherwise known as the midpoint of a side of the triangle, you are cutting the area of the triangle in half. Here we have a red line from the right-hand vertex to the bisector of the opposite side, where the cyan bisects it, a blue line from the bottom left vertex to the point where the yellow bisector bisects the side opposite that vertex, and a green line from the top left vertex to where the magenta bisector bisects the side opposite that vertex. Three bisectors that are they're not angle bisectors and they're not perpendicular bisectors of sides, they are vertex to midpoint area bisectors. Well, if each of those is cutting the triangle in half in terms of area, then each side of each of those lines is equal area. So at that point where they all cross, there is equal area, both sides of it, in all directions, making that the centre of gravity of the triangle. I think some people call it centroid or something, maybe that's the author, I don't know. But anyway, there's your centre of gravity. If this was a steel plate triangle, that would be the point where it balances. Slightly prettier version without all the extraneous lines. Special case, a right angle triangle. In this case, a line from the top left vertex and perpendicular to the base is the left side of that triangle, or rather, the left side of that triangle is part of that line, and the base, the bottom side of the triangle, is a line perpendicular to the left side, passing through the rightmost vertex. So you only need to draw in one more perpendicular from that bottom left vertex through the long side of the triangle to get your orthocenter, which is the vertex of the triangle at which the right angle exists. And another special case, an equilateral triangle, a triangle with sides 1, 1 and 1. So we all know what the angles in those vertices are, don't we? Don't we? This is a special case in which all the centres are the same place. We have red, green and blue lines from vertex, perpendicular through midpoint of opposite side, all three ways. So each of those is the perpendicular bisector of the side, the angle bisector at the vertex, the line from vertex to midpoint of opposite side, and the line from vertex through opposite side at a right angle. And they're all the same line, so all the centres are in the same spot. The other thing you might spot here is two circles, both looking fabulous. The incircle and the circumcircle, and yes, they really are exactly 1 to 2 ratio of radius. Because the radius of the incircle is the shortest side of one of these 30 degree, 60 degree and 90 degree triangles, of which there are 6 within our big 60, 60, 60 triangle. And the ratio of the, and the radius of the circumcircle is the length of the hypotenuse of one of these 30, 60, 90 right angle triangles. Which means the ratio of the radius of the incircle to the radius of the circumcircle is going to be the ratio of the opposite to the hypotenuse of half the angle in the vertex of an equilateral triangle. In other words, it's going to be the sine of 30 degrees, which is 0.5. And I apologise to anyone whose eyes are getting sore right about now, because this just went light mode. Practical use for this skill, or at least one of these centres, apart from finding a balance point of a triangular steel plate. One rifle target. One really nice bit of shooting. They've all gone through the 10 ring. There's a 10.1 in the centre. If you're shooting 5 or 10 shots, that's fine. If you're shooting 20, you might want to score it as 10.05 because it's meant to be a tiebreaker. So the maximum possible score with 10 shots is 101. Maximum possible score with 5 shots would be 50.5. If you miss the 10 ring, you lose a whole point. You can't make that up by getting the rest of your bullets through the 10.1. But anyway, 4 of those are actually inside the 10.1, but another 2 have broken it, and by convention they score that as well, so this group scored 100.6, which is very nice. But that's scoring, not group size. What if you have to group size? Or what if you lend your rifle to someone and, well, up in the top left, we have someone who apparently uses thumb over bore. This is someone who has wrapped his thumb over the top of the rifle barrel and pressed it down hard against the grip and put enough of a curve into the rifle barrel to actually move his group high and left. It's a fairly good group. We can find that centre of it with a 30 pixel diameter. Do wish people wouldn't do that with my nice rifle. That's actually quite a long way for it to shift because of that. I have seen a shift that would maybe from 8, maybe it would move the centre out into the 8 ring at about the 10 o'clock position, not all the way out to the 5. Because I was shooting hand underneath grip and the sights were set 0 by someone who shot thumb over bore, so I was shooting the 8 ring at the 4 o'clock position. Different group over here, which is just a lousy group, 80 pixel diameter. And down here we have me, with my lovely tight group with a 29 pixel diameter. Because I am the best. Gold medal. Rah. All well and good. These are all done as circumcircles. You pick the 3 outermost points, outermost bullet holes, marked with green dots here. And then I have pairs of green arcs for the rightmost triangle, most side of this, pairs of orange arcs for the top left, and pairs of, and for some reason, orange and blue crosses for the bottom left side of this, giving me the circumcenter of a triangle of those 3 outermost bullet holes, but that includes all the others. So that's cool. Over here we have blue arcs around the bottom left bullet hole, green arc around the top bullet hole, and orange arcs around that bottom right bullet hole, giving me again a circumcenter and a circumcircle that includes all the other bullet holes as well. So that's fine. And if we come down to my excellent shooting down here, you can see yellow arc around the top left bullet hole, cyan arc around the top right, and magenta around the bottom. Then white perpendicular bisectors of the sides through the cyan and yellow crosses for the top side, through a cyan and magenta cross for the right hand side, and through a cyan and yellow cross, through a magenta and yellow cross for the left side, giving me a circumcenter and that lovely tight circle, which again includes all 10 bullet holes. So this is great, although at this scale you might start having trouble drawing it all that precisely. Very sharp pencil. It can be hard to say exactly where the centre of a bullet hole is, but then we come to a problem. This guy. Now I can tell you why this group is this shape. This person doesn't have good breath control. When you breathe in, your chest gets bigger, which lifts your body, which lifts the back end of the rifle. Rifle pivots on the forward hand that's holding it, and the muzzle goes down, and you shoot bottom left. As you breathe out, the back end of your rifle sinks back down, and the muzzle swings up and to the right, and you get this line. You're supposed to, breathe halfway out and pause and see where it aims and adjust, your legs first, then your arms, and then your hands, and then just your fingers, and then your fingertips, until it's naturally pointing at the centre, and then you breathe that far out and pause and shoot, and then let the bullet go, and then release the trigger and breathe out the rest of the way. Breathe in and out and in, and breathe halfway out, take up the slack, breathe out, breathe in, breathe halfway out, squeeze it the last bit of the way, pause and let the bullet go, and then breathe out, breathe the rest of the way out and release. What this guy was doing was just breathing and shooting. It's faster, but you get this diagonal stripe effect. And the problem here is that this we need to measure the group size here to see how well this guy did compared to the other shooters. Now if I try to do the circumcenter of this, I've got the 2 ends of the longest side of the triangle. They're fairly obvious. And I've drawn green arcs around the bottom left point and orange arcs around the top right point. The question of which point to use as the other vertex of the triangle, that's a bit trickier. I've chosen one in the middle, and I get these purple lines way off to the top left, which don't really line up in the same place, because being out by a tiny bit on that on the arcs, on centering the circle I used to draw those arcs, it throws these lines way off. So you have this mess, but I have managed to draw a purple circle somewhere. My bad. Seem to have lost the purple circle. The problem here is that you get a purple circle with a diameter that's several hundred pixels, because your centre is way off to the left there. So if you work it out as a circle of this triangular group, depending which you choose as your third member of the group, your centre could be somewhere in the 8 or the 7 or the 6, or way out in the no scoring area, which obviously isn't the centre of your group. So alternative approach. We don't have a third point. We draw a line between those two, the top and bottom bullet holes in this case, the most distant pair of bullet holes, and we construct the perpendicular bisector of that, just one green arc around, well, one green arc each side, around that top bullet hole, one orange arc each side around the bottom bullet hole, crossing those green arcs. And then we draw that magenta line across those two crosses, and where it crosses the red line linking our two bullet holes, that's the midpoint of that line. We have the perpendicular bisector of one side of a triangle, and we just ignore the other two sides in the vertex and use the midpoint of that line as the center of our circle. And then we can draw in this circle only has a diameter of 56 pixels, which ain't wonderful, but it beat the guy in the top right, which I think is fair. That is a better group.